Welcome to Chemistry Lover, and in this video I'll be talking about a very important name reaction, which is the Hosomi Sakurai reaction. As you can see, this is the reaction. This is basically the annihilation of different electrophiles. For example, in this particular case, I have chosen the alpha beta unsaturated carbonyl compound. You may have any other electrophiles like normal aldehyde or ketones or epoxide or anything like that. But why this particular reaction is so important? Because here you have to predict the correct regioselectivity, right? And this question is actually from the csir-net exam December 2018. Now, as you can see, it is also promoted by this Lewis acid. Like here we have used the titanium tetrachloride. So if you don't know the specialty of the allyl silicon reagents which is used here, and if you just know the reaction of Grignard reagents, then you will predict the formation of this product, which is a result of 1,2 addition or direct addition on this carbonyl group. Because you know, these Lewis acids, they promote the electrophilicity of this carbonyl group by forming the complex like this, we can say. So it is like Cl4. So here by this complex formation, delta positive generates here, and this in turn withdraw electron from here, and here you will also have delta plus. So it increases the reactivity of this particular carbonyl carbon, and that will favor attack over here. And if you use a Grignard reagent, for example RMGBr like this, then yeah, so the reaction will be favored on this 1,2 position. But with this silicon reagent, you will not get this product. Instead, what you will get is, you will get a product like this. So here you have 1 2 3 4, so 4 carbon, 1 2 3 4, and you will have a product like this. So now it is 1 2 3 4 5 6 7. So 1 2 3 4 5 6 7. So you will have a product like this. So you can see this is a result of conjugate addition or 1,4 addition on this alpha beta unsaturated carbonyl compound. Now the real question is why this 1,4 addition happens and not the 1,2 addition, although the Lewis acid is given here. So for that you have to understand the phenomenon called the beta silicon effect. Now what is beta silicon effect? So and this is where the difference in reactivity between a Grignard reagent and a alkyl silicon or allyl silicon reagent. So in Grignard reagent, what happens, this metal carbon sigma bond, this sigma bond, they directly attack, right? But in case of silicon reagent, this sigma bond is not the electrophilic center, nucleophilic center. This sigma bond is not the nucleophilic center of the molecule. Rather than this pi bond is the nucleophilic center here. Why this is so? So this is because, so if you consider this structure, you can see, so here you have the pi bond, and here you have the silicon group like this. So it is the sigma bond. So it is the sigma bond. So this is basically CSI sigma, okay, and this is the CC pi star, right? This is the CC pi star and this is the CSI sigma. Now you can see they are parallel and there may be a overlap between them, right? So their symmetry will be matched and there may be a overlap like this. So if the symmetry be like this, then there will be, so between this sigma and this CC pi star there will be overlap, and that increases the energy of this pi bond. So if it push electron to this pi star orbital, the energy of this pi orbital will increases. So this pi orbital or this pi bond, that will that is basically the HOMO of this molecule, and now the energy of this HOMO rises. Okay, so that's why this pi bond, so if you consider a normal alkene and a allyl silicon compound like this allyl silicon compound is much more nucleophilic, is a better nucleophilic than a normal alkene. So they prefer to attack on the electrophilic center. But this increase in reactivity is not so much high that it can attack on uncatalyzed or unactivated electrophile. For example, a normal alpha beta unsaturated carbonyl compound or a normal carbonyl compound. It needs a Lewis acid catalysis like this. So if this Lewis acid catalysis happen, then due to this interaction, so you can also write it like, so you can write it like this also. So here it is like TiCl3, and now here you will have a distinct positive charge. And sorry, I actually did a mistake. I have this. Okay, so I did a mistake, forgive me for that. So here basically you should have this. Okay, this. So I just put one carbon extra. So now you can see there will be a resonance structure. It will have a resonance structure like this, where the positive charge will be here, TiCl3. Now you can see this is how it activates this electrophilic center, and now this pi bond can easily attack over here. Now the question is, why this pi bond will attack on here and not this more activated carbonyl compound? So for that you have to know the difference between 1,4 addition and 1,2 addition, and I made an entire video on that. You can watch this, the link is in the description section, but I will take 2 points from there. One is the 1,4 addition or the conjugate addition, that is controlled by the size of the orbital, the extent of overlap, and so the how good a particular orbital in overlap, and the extent of 1,2 addition is controlled by the charge. Now you can see here the attacking center is basically a pi bond which doesn't contain any charge, right? So it is a pi bond, the attack happens from here. So for this pi bond, the orbital interaction is the most important factor, not the charge factor. So although this carbon is more positively charged, because this nucleophile doesn't involve any charge, so the charge factor is not important here. The important factor here is the orbital interaction. And you know that for an alpha beta unsaturated carbonyl compound, this particular center has the highest coefficient of LUMO, and that means this position will be far better at overlap with any nucleophile than any other center. So that's why it will prefer to attack over here, because of this orbital overlap. And now let me show you how this reaction actually happen. So from here this attack takes place, it goes like this. So now you will have, so here you will have a positive charge, sorry, let me draw it again. So there you will have a positive charge, and now the attack take place here. So here you have TiCl3, this, and now here you have Si Me3. Now what happened next? So by this attack you can see one Cl minus is removed, there Cl minus will come back, it will attack over here. Now it will go here, so you will get this, and now here the tautomerization can happen to give you this carbonyl compound. So this is how you will get this particular product, you can see. So what we have learned from this particular reaction is that although the reaction is Lewis acid catalyzed, but 1,2 reaction is not favored because of the nature of the nucleophile, which is a soft nucleophile, which for which the orbital overlap is most important than the charge interaction. And that is the take home message from this particular reaction. I hope that you understand this concept, and if you are new in this channel, then subscribe my channel. Thank you for watching.